There are these invisible guardians all around us, protecting our electrical grid every single second of the day. They're constantly on watch, ready to stop a single little spark from becoming a massive, city-wide catastrophe. Today, we're going to pull back the curtain on one of the most important of these guardians, overcurrent protection. So, let's kick things off with this one big question. When something goes wrong on a power line, say a tree falls on it or a wire shorts out, what exactly stops that one single problem from cascading and taking down an entire city? The answer, as you're about to see, isn't just about stopping the fault. It's about doing it with almost surgical precision.
All right, here's our game plan. First, we'll talk about the threat itself, what an overcurrent actually is. Then, we'll get into this really cool principle of isolating the problem, the strategy behind it, this idea of a ticking clock for equipment damage, and finally, how it all comes together in what's like a coordinated dance.
So first things first, let's talk about the threat. To really get why the solution is so elegant, you have to appreciate the raw, destructive power of the problem we're trying to solve, and that is the overcurrent.
Okay, so an overcurrent, it happens during a fault, like a short circuit. And look, we are not talking about a small little spike here. The fault current is just worlds apart from the normal, everyday current flowing through the line. Seriously, think of it like this. It's the difference between water flowing through a garden hose and a fire hydrant suddenly bursting through that same pipe.
So why is this type of protection really the bedrock of grid safety? Well, because it's just beautifully simple and effective. It's the easiest and cheapest way to guard the entire system. You find it everywhere, from these huge power plants right down to the circuit breaker in your house. And the most crucial part, it acts incredibly fast to stop catastrophic damage in its tracks.
Now, just detecting a fault, that's not enough, right? If your toaster in the kitchen causes a short circuit, you definitely don't want the entire neighborhood to lose power. What we need is an intelligent, super localized response. And that is where this principle of discrimination comes into play.
The whole goal here is to isolate the fault with precision. This means the protective relay, which is kind of the brain of the system, tells only the circuit breaker that's immediately upstream of the problem to open up and cut the power. Everything else on the grid, it should stay on, completely unaffected, just delivering power like nothing ever even happened.
So how do we actually do this? Well, the two classic ways are based on either time or current. With time, you just set up a simple delay system. But the problem is, a massive fault right next to a power plant can be allowed to rage for several seconds, which is an eternity in the electrical world, while it just waits its turn. It could cause incredible damage. With current, you get speed, which is great, but it's not always reliable. It really depends on where the fault is. So you see, neither one is perfect on its own. We need something a lot smarter.
So, what if we could combine the best parts of both of those methods, but get rid of their drawbacks? Well, this is where the modern strategy gets really, really clever. It's all about blending time, current, and this concept called curves.
We can get the best of both worlds by using something called an inverse time characteristic, and it is such an elegant solution that dynamically links how long it takes to trip to how bad the fault actually is. The principle behind it is actually pretty simple, but it's so powerful. The time it takes for that protective relay to act is inversely proportional to the current. So a small overcurrent might be allowed to hang around for a few seconds. But a massive, massive fault current, that's going to cause a trip almost instantly. The bigger the problem, the faster the response.
And we can see this whole relationship on a graph, which we call a time-current characteristic curve, or a TCC curve. It's pretty simple. You've got time going up on the vertical axis and current going across on the horizontal. Any fault that lands up in that relay operating region, meaning it hits a certain current level for a certain amount of time, is going to trigger that device to trip.
Okay, so why are these curves so incredibly important? Because they are not just some abstract lines on a graph. No, they represent the razor-thin margin between a safe power system and millions of dollars of burning equipment. This is the ticking clock.
Think about it. Every single cable, every transformer, every generator out there has a physical limit. It can only handle a specific amount of overcurrent for a specific amount of time before it suffers permanent, catastrophic damage. And that limit is what we call its damage curve.
So if we look at a typical power cable, for example, its thermal limits break down into 3 zones. You've got ampacity, which is just its normal, safe operating current. Then there's an emergency overload zone, where it can handle a bit more for a short time. But then there's the short circuit damage zone. That's the red line. That's the point of no return. If a fault pushes that cable into this region, it starts to physically break down. So the entire job of a protection engineer is to solve this one big puzzle. They have to program the protective relay's inverse time curve so that it sits perfectly in that gap. It has to always operate before the equipment's damage curve is ever reached, but it must never operate during just normal, everyday conditions. And this right here, this is what that perfect balance looks like. The protective curve is so carefully engineered to live right in that sweet spot. It's fast enough to prevent any damage, but it's also just slow enough to avoid any unnecessary blackouts. This is the absolute key to getting both maximum equipment protection and maximum customer reliability. So when we put all of these pieces together, what we have is not just some simple switch. No, we have a highly intelligent, coordinated system that performs this really intricate dance to keep our power flowing safely and reliably. See, across the entire grid, each one of these protective devices is carefully graded. This means that response curves are intentionally stacked and timed relative to each other. By coordinating the curves of all the devices upstream and downstream, engineers create this cascading defense that makes sure only the device closest to the fault operates, and for exactly the right reason. And really, that's the key takeaway here. Overcurrent protection is not some brute force tool that just stops faults. It's a really sophisticated system that's built on a very delicate balance. The balance between protecting incredibly expensive equipment from damage and ensuring that reliable flow of electricity that, powers our entire lives. But this all leads to a final, really big question. For about a century, this whole system has worked beautifully for power that flows in one direction. But now, as our grid gets more and more complex, with power flowing in multiple directions from things like solar panels and wind farms, the very idea of upstream and downstream starts to get, well, a little blurry. So how will these fundamental principles of protection need to evolve to keep the lights on? Well, that's the challenge for the next generation of engineers.